This video is a walkthrough of how you might solve a projectile motion question. This is the example 1 from the practice problems that I gave you, and it reads that Super Dave is fired from a cannon inclined at 48 degrees to the horizontal. If Super Dave leaves the cannon at a speed of 18 meters per second, then we're asked to find certain things. A, how high did he go? How long will it take him to reach the maximum height? And where should he instruct his team to put the net to catch him? In other words, how far will he travel? So let's first just make sure we can visualize exactly what's happening here. So we'll draw a picture of it. We know we have Super Dave coming out of a cannon. So there's the cannon. And here's the little head there, okay? And we know that he was fired at 18 meters per second. And we know that it was at an angle of 48.0 degrees, okay? Now, if this is a typical projectile, he's going to fly out, he's going to rise up to a maximum height, and he's going to come back down to the ground. So there's a few things that we're going to need. And as was looked at in the question, how high did he go? So essentially it's asking us to determine this. Just pick a different color than that. Okay, they want to know how high, which is going to be his vertical displacement, delta dy. How long will it take him to reach there? So it's asking us to find length of time. All right, so we're all also interested in how long it takes, at least to get to the maximum height, to get from here to here. And finally, we're interested in his range. How far will he travel? Essentially, it's saying where should he instruct his team to put the net. Okay, so we're looking at this value over here, delta dx. Okay, so in almost every projectile motion question, we are given an initial velocity and an initial angle. Now, we know from our understanding of projectile motion that the fact that this was 18 meters per second is really not useful information to us, because what we really want to know is we want to know horizontal and vertical information, right? So how fast was he traveling in the x direction, and how fast was he traveling in the y direction? So what we need to do is we need to take this main vector here, 18 meters per second at 48 degrees, and we need to convert it into its horizontal and vertical components. So let's first do that. We know that the horizontal component, Vx, is going to be equal to the V initial, in this case multiplied by the cosine of the angle. So that gives us 18 multiplied by cosine of 48 degrees. And that works out on the calculator to 12.044 meters per second. And I just want to point out here, this is something often, if your calculator is in radians instead of degree mode, then you're not going to get the right answer. So this is not, everything needs to be in degree mode, so make sure that you do not have your calculator in radians, otherwise the calculations won't work. So now we know what the horizontal initial velocity is. We're going to need this number later, so 12.044. And let's calculate the initial vertical velocity. So let's do the same sort of thing. We know that Vy is equal to the initial velocity times the sine of theta, which in this case is 18 meters per second times sine of 48 degrees. And we determined that it's 13.377 meters per second. Okay, and that's our initial vertical velocity. In other words, we know that given this vector, in the x direction, the motion is around 12 meters per second horizontally and around 13 meters per second vertically. Okay. Now, the next most important thing to do is to identify variables. We've drawn a picture, we can visualize it, we've determined our vector components. Now let's outline all of our variables. Now, what happens different in a projectile motion question is that we want to keep our x variables completely separate from our y variables because, as we mentioned, x and y are independent. So we know that the motion in the horizontal does not affect the motion in the vertical. So what I'd like to do is I like to outline all my variables like this. And let's put our x variables here and our y variables here. Now, in the x direction, there are no forces in the x direction, so really we're just looking at uniform motion. There is nothing speeding up or slowing down the projectile. So the only three variables are the ones pertaining to this equation. Uniform motion's velocity is displacement over time. And so the only ones we can really worry about are delta dx, delta t, and vx. Okay, and we actually know what those numbers are from our last slide. Our horizontal velocity was 12.004 meters per second. We don't know anything about the time, so we're going to leave that as a question mark. And our displacement in the x direction is what we need. Okay. Now, given that the only possible formula for us to use is this uniform motion equation, then if we wanted to solve for delta dx, we would need to know both vx and t. And since we do not know what the time value is, we cannot solve for this displacement in the x direction. It can't be done yet. So we're going to have to leave that part. That's part C of the question. We're just going to leave that right now because we recognize right away there's not much we can do about it. Now let's look at our y direction. In our y direction, we have acceleration. Gravity is slowing down objects that move up and down. So instead of just those three variables, we actually have 5 variables. Vi in the y direction, Vf in the y direction, acceleration in the y direction, displacement in the y direction, and time. Now, you'll notice that I haven't been putting x's and y's on my time, and that's because there's no such thing as horizontal time and vertical time. Time is independent of any of the direction. So here's what we know. We know that the initial velocity in the y direction was 13.377 meters per second. We also know that when the object comes to the very top of its motion, right, from the bottom of the projectile straight through, okay, at the very top of its motion is the moment at which the ball stops rising and begins to start falling. Okay, so that means it's moving up, it slows down, it slows down, it slows down, it comes to a stop, and then it begins to accelerate back to the ground. So the final velocity in the y direction, in this case, at this position in the motion, is 0. Now, what's causing it to slow down? Well, we know that's gravity, so we can put in here 9.81 meters per second squared down. Incidentally, this is an upwards vector. Now, displacement in the y direction, that was what we were asked to find, because we're looking for the maximum height, so this is what we need. And the time, we don't know anything about the time. Okay? Now, let's look at these variables, because we can begin to solve part A if we notice that we have VIY, we have VFY, we have AY, and we need to solve DY. So really, to solve part A of the question, we are looking for an equation that solves for D, but that does not include T. We do not have T as accessible to us. So we're going to have to find the right equation, and I'm going to pull one out here based on the 5 kinematics equations that we've looked at already. So the only equation that does not have t in it from our kinematics equations is this one. Vf squared, and we'll do y direction, equals Viy squared plus 2 acceleration displacement. So let's substitute in what we know from our numbers. The final velocity was 0, and the initial velocity was 13.377 squared. Notice I'm keeping a fair number of digits around. We don't need to actually have that many digits in our final answer, but the more digits we can keep throughout the question just gives us a more accurate answer at the end. We're really going to round at the very end, so we like to keep extra digits around until that point. Okay, so plus 2 times the acceleration, which we know is negative 9.81, multiplied by the displacement in the y direction, which we don't know. Okay, so there's really only one unknown variable. We can rearrange this equation. We'll start by squaring this result. We're going to bring it over to the other side and change its sign. We'll divide by 2, divide by negative 9.81, and we'll isolate delta d. So what we get is this. Delta dy 13.377 squared, that's going to be negative because we bring it to the other side, divided by 2 times negative 9.81. And finally, our answer then is delta dy equals approximately 9.12 meters. Okay, that's a positive number, so we know it's up. Okay, so our official answer to part A is that therefore Super Dave will travel 9.12 meters up. Okay. So we just determined the maximum height. We figured out that delta dy was 9.12 meters up. That's his maximum height. But part B then asks us how long does it take Super Dave to reach the maximum height? So now in this case, we actually are looking for time. So we can go back to those values that were given in our chart. Again, we know what initial velocity in the y direction is, we know what final velocity in the y direction is, we know what acceleration in the y direction is, and we now even know what displacement in the y direction is. So we have 4 out of the 5 variables. There's almost any equation we can use to solve for t. Personally, I prefer to choose an equation that doesn't actually depend on d. And the reason I do that is because if I made a mistake calculating this value, then I actually don't want it to affect the next part of the question. So I'd rather just base my equation on the values that were given in the question rather than the values that I've since calculated. So the best bet in this case is the acceleration formula. df minus vi over delta t. And in our case, we know all of these values here. We know negative 9.81, the final velocity is 0, the initial velocity is what we calculated, and so we can actually solve for t. So let's rearrange that and do that. Delta t equals, we're going to have 0 for final velocity minus 13.377, all divided by acceleration, which is negative 9.81. And so as our final answer, we would get approximately 1.364 seconds. Okay, so again for part B, we then say, therefore, it will take Super Dave 1.36 seconds to reach max height. At this point, we're almost finished the question. The last part of the question said, where should he instruct his team to put the net? So here's our projectile motion again. Here's some of the things that we are looking for, delta dx. We know delta dy, that was something we were able to calculate, so we know this height from here to here. We also happen to know the time it takes to get to here. We figured out the time it takes to go from initial to its maximum height. Now if you look at the motion of a projectile, if we start and end on the very same level, so there's no drop in level, then the amount of time it takes to get to the top is also the amount of time it will take to fall back down. So we go back to our initial equation for horizontal motion. Remember, horizontally we just have uniform motion, and so the only equation that applies is this one. Velocity in the x is displacement in the x divided by time. And so I'm going to rearrange that to solve for displacement. Delta dx, which is what we need, is velocity in the x times time. And the velocity in the x, if you remember, was 12.044 meters per second. And the time that it takes is simply going to be double the amount of time it took us to get from here to here, which, if you remember, was 1.364 seconds. Okay, so we'll double that. All right, so 2.73. We do the multiplication, and we end up with 32.847 meters. So we finish off the question by saying, therefore, Super Dave should put the net 32.9 meters, and then we can say east or to the right of his start. Okay, so all in all, there's been a lot that we've covered there, and so you may want to review this video a few times, and certainly practice will be the key. So make sure that you've gone through all of the projectile motion practice questions that I've posted, and they will all have a similar look and feel to this. Remember, if there was any sort of series of steps I'd like you to follow, it would be this. Step number 1, draw it. Okay, once again, if you can't visualize what the question is asking, then you're going to have a very difficult time actually trying to solve it. Almost all questions will involve vector components, so I'm going to say break down break down your vector components. Remember, we're not interested in the original vectors, we're only interested in the independence of x and y, so we have to solve x direction and y direction separate from each other. Number 3, you're going to do identify your variables, and I'll put x and y variables because they have to be done separate. And 4, now you're just going to solve, and that's using your kinematics equations. Okay, so best of luck with the process there, and as before, feel free to email me if you're struggling with some of the questions and you want some extra help. Good luck.